language models are rapidly evolving into AI agents capable of reasoning, planning, and interacting with external tools. While these capabilities increase usefulness, they also introduce new security risks. In this video, we explore UDora, a novel red teaming framework that demonstrate how attacker can manipulate an agent's reasoning process itself, causing it to perform harmful actions. Unlike traditional chatbots that simply generate text, modern AI agents perform multi-step intelligent flow before taking action. They can search the web, access email, execute code, and interact with external systems. Because actions are derived from reasoning, attacker may target the reasoning process instead of the final response. Existing attacks such as prompt injection attacks are the attacks that are unreliable. And jailbreak techniques targets the output of the model. Okay, this both mainly focuses on manipulating the final output of the LLM model. As you can see, however, agents first reason, then plan, and then execute the action. Firstly, they will make some reasons, then they will plan what they have to do, then execute their action. As a result, traditional attack often fails. This create a research gap. What? How can we systematically manipulate an agent's reasoning process to trigger malicious actions? This paper matters. This is because AI agents are increasingly deployed in real-world systems. If an attacker can manipulate an agent's reasoning, they can hijack before they act. They can, if an attacker can manipulate an agent's reasoning, they may gain access to the private emails, like email data leakage can be happen. They influences the wrong purchasing of the items in the shopping by the shopping agents and web agents. Also, harmful web actions has been taken due to the security breach, and privacy violation also happens. This or many more harmful actions have been occurred. So understanding this vulnerability is essential for building secure AI system. LoRa operates by observing the reasoning. This is generated by an agent. It identifies the important locations within the reasoning trace, inserts target information such as tool name, and then optimizes an adversarial string. Over multiple iterations, the reasoning gradually shifts toward the attacker's desire. The logic part, UDora has two optimization modes. First is sequential optimization and second is joint optimization. In sequential optimization, it modifies reasoning position one by one, while, op while the joint optimization updates multiple positions simultaneously. This approach allows the attacker to adapt to different reasoning style and agent architecture. Experimental setup to evaluate the effectiveness, the author tested UDora in the three benchmark dataset. First is inject agent. Inject agent focuses on prompt injection. Then web shop evaluates shopping agent and agent harm. This agent arm measures harmful behavior. The performance of this dataset are being measured using attack success rate indicating this indicates how often the attack successfully manipulates the agent. And the models that we have used in this experiment is Lemma 3.1 and Mistral 8B. Now the experiments shows some of the results like UDora has been consistently outperforms existing attacks. As you can see in this graph, on inject agent, it achieves remarkable 99% attack success rate. Now similarly, the improvement has been seen in the web shop and agent harm. Web shop has the attack success rate of 61.75% and agent harm has 97.7%. Inject agent and agent harm are not so different, but according to the inject agent harm is has attack success rate is less. So this demonstrates the effectiveness of reasoning aware attack across desired environment. Has demonstrated some of the real world case study and also give some limitations on this. First, we will talk about the real world attacks. In this, email assistant powered by GPT-4o and Gmail tools, the attack successfully extracted private information despite safety instructions. However, the UDora has announced some limitations also. This includes dependence on token probability access and assumptions about model eternals. This means that this type of attack, this type of insecurity needs some token probability and should have strong model access assumptions and should limit the process diversity. So, the future scope and key takeaway of this paper is first we will go to the future research work. The future research can be done in the black box, which is the reasoning attack, better defense mechanism to develop adaptive and robust defense, multi-agent security for the multiple attacks, and reasoning verification system. The key takeaway of this paper is the reasoning itself is an attack surface. This is the important point of this. So the key contribution of this paper is the realization that reasoning itself has become an attack surface in AI agent. The future work should focus on the black box attack, strong guardrails, reasoning verification systems, and security mechanism for multi-agent environment. As AI agents become more autonomous, protecting their reasoning process will be as important as protecting their final input. Sorry, output.